All right, let's talk about Euclidean domains. So a commutative domain, so we have a commutative ring with no zero divisors. We say that's Euclidean if we have a function from non-zero elements to positive integers. Of course, we wouldn't write n here because n, or boldface n, does not include zero. So we include integers greater than or equal to zero. So it's a function such that for every single element of the ring and for every single non-zero element of the ring, basically we have a Euclidean algorithm, which is similar to the Euclidean algorithm that you'll see for integers in like a first abstract algebra course, or maybe like a group theory course we might talk about it. So basically, for every single a and b like this, there is some q such that we can write a as qb plus r. R here, of course, is the remainder. So either r is going to be 0, i.e. we have 0 remainder, and a is just a multiple of b, or r is going to be less than b. So basically what we've done is we've reduced the remainder has like small size relative to what we're dividing by. And so of course the typical example of this is you let the ring A be the integers, and this distance function is just the absolute value. And we don't include 0 in this distance function because things start to sort of break down there. So you're a lot of times, like another example of this would be if we let A be a ring of polynomials and we let this delta be the degree of the polynomial. And in that case, a lot of times what I've seen is that you can define the degree of the zero polynomial to be negative infinity. And so then what happens there, this is of course polynomials in one variable, and what happens there is that it works because if you add two polynomials, the degree of the sum is just whichever, it's the degree of the polynomial which had the highest degree. But when you multiply together the degrees. So if you take a polynomial of degree 2 and a polynomial of degree 3 and you multiply them together, you get a polynomial of degree 6. And that's exactly what happens when you... No. You add them together. What am I doing? Right, because x squared... Yeah, because exponents add together when you multiply. So degrees, if you multiply two polynomials together, then the degrees add together. And so that shows you why you use So if you consider a constant polynomial has degree 0. And if you multiply a polynomial by a constant, its degree doesn't change. And that makes sense because you're just adding 0 to the degree. And then for minus infinity, if you take any polynomial and multiply it by 0, you get 0. And in a similar sense, if you look at the degrees, you're taking some finite number and adding negative infinity to it, and then you're always going to get negative infinity if you define addition that way. And so it works out that way. So yeah, that's what you'll typically do. Anyways, so that's what a Euclidean domain is, and they are PIDs, i.e. principal ideal domain. So every ideal in a Euclidean domain is generated by a single element of the ring. So to prove that, take any ideal A in a Euclidean domain, and we want to prove that it's generated by one element. So choose some B in some non-zero element B. Let this be an element of smallest degree. And why can we do that? Well, certainly, whenever you're looking at like a min over like a set which has size that could be, we know nothing about the size of this ring. This ring could be like super uncountably infinite, which isn't a thing, but it can be uncountably infinite. But the thing is, this function delta takes values in positive integers. So you can just sort of look at the inverse, like, you know that there's going to be some non-zero element in this ring A, and that non-zero element will have some value at delta, which will be some positive number. And then you just look at that one, and you look at the inverse image of all of the integers less than this, and if all of those inverse images are empty, then you're good. If they're not, then you just choose some element there. And so because there's some choice here, we didn't talk about this. I wonder if you actually use the axiom of choice here. Because we're choosing an element from a possibly uncountable set even. So that's something that, like, when you study a lot of math, you might, like, when you're making a choice of something, you always have to be really careful, because there should be like a red light that goes off in your head, like, we might be using axiom of choice here. Typically, we don't really care in practice, because we'll just either assume axiom of choice or like not use arguments that involve it. But this seems to be a case where I wonder if we do have to use the axiom of choice. I could be entirely wrong though. But anyways, moving on. Just the fact that you're choosing something. So certainly we have the ideal generated by the single element B is contained in A. So that's just because it's an element of A, and it's going to be, if you take any element in an ideal, the ideal generated by that element will be contained in the overall ideal. That's very straightforward. So the reverse inclusion is trickier. So, well, a little bit. Choose an element A, which is in A, and because we have this Euclidean algorithm, we can sort of divide. What we're doing here is we're basically dividing by B with remainder. And so we can find some Q that allows us to divide A by B with remainder R. And either R is going to be 0 or delta R is going to be less than delta B. Now the latter is impossible. And why is the latter impossible? The latter is impossible because if we move this QB over to the other side, then what do we have? We have A, which is an element of A, and we have Q times B. Well, B, we know, is an element of A, and we're just multiplying it. Like, once we've moved it over, we're taking this element and multiplying it by negative Q. But because it's an ideal, multiplying by elements keeps you in the ideal. So negative Q times B is in the ideal. So A minus Q times B is in the ideal, and so R is in the ideal A. And so, speaking of which, should be the min overall alpha non-zero elements in the ideal A. All right, so yeah, so R is in A, and let's see here. If it were the case that R is not 0, then it can't be the case that delta R is less than delta B, because that would contradict our choice of delta B. So the latter case is impossible, and so R is equal to 0. And so what does that tell us? That tells us that if R is equal to 0, then A is equal to Q times B, meaning that A is a multiple of B. And if A is a multiple of B, that means that A is in the ideal generated by B. And this holds for every single A, and that implies that this ideal A is contained in B, in the ideal generated by B. So, and combining this with this inclusion tells us that the ideal A is the ideal generated by B. And so this ideal A is generated by a single element, i.e. it is a principal ideal. But this holds for every single ideal in the Euclidean domain, and so it is a principal ideal domain. That is a lot of so's in this sentence. That's kind of cool. But anyways, so yeah, so Euclidean domains are PIDs, and the converse is not true, because if the converse were true, we wouldn't have two different definitions. But it turns out the simplest example is this weird thing. You take integers, but you also adjoin the element 1/2. You take the what is this, the field or the ring, the ring that you get when you take the integers and you add in an element 1/2 times 1 plus the square root of -19. And yeah, that's sort of cool, I guess, that exists, but it's just sort of like, I don't know, like this should be sort of like the thing that's sort of like, wow, that's really interesting that such a thing exists. But I feel like there's so many really cool, interesting facts in mathematics that your like tolerance for getting wowed by stuff starts to build up. And so when I see something like this, I feel like this doesn't really wow me the way that it would have when I like first started getting into math, because I look at this and I sort of think like, wow, that probably takes a lot of work to prove, and that does not seem like it would be a lot of fun. But anyways, this is sort of an interesting thing, and things like this, like if you do find this interesting, then things like this can be really helpful in motivating you to like learn more about this stuff, and get to the point where you can see why such a strange looking thing might be true. But also this is in some sense the simplest PID. Like apparently there's like a whole family of like examples of this type, and people study these. But apparently this is like the simplest one, like maybe using the simplest formula. I don't know what sense of the word simplest this is, but that's just something I heard from my algebra professor, and I trust him on that. So, fun fact. All right, so let's talk about polynomials in several variables. It's basically just exactly the same thing as in one variable, but we have several variables. So we take alpha is a multi-index, so alpha 1 through alpha n are elements, integers which are greater than or equal to 0, each of these individually. And for each multi-index a, we get a particular constant, and we multiply it by x to the alpha. And x to the alpha is x1 to the alpha 1 times all the way through xn to the alpha n. So we take all possible powers of the xi's to different integer powers which are greater than or equal to 0. So all sums of this form where the x alphas look like this, and we also have the condition that all but finitely many of these constants are 0, which means that the sum here is finite. All right, and we do multiplication in the same way that we have the sum of these integers, and like this this polynomial times this polynomial. Here I just dropped out this z thing. That's going to be in there. That's sort of implicit. We have this sum, and then you just take the sum overall. Again, this is gamma in z greater than or equal to 0 to the n. Then all multi-indices alpha plus beta, which sum to gamma, a alpha, b beta, then x to the gamma. By the way, it sounds like, I hope there's not too much like growling going on. I think my neighbor just got a dog, and it like barks sometimes. So it's like the worst parts of having a dog. Like I hear like the barking, but I don't get to like pet the dog or play with the dog. So it's kind of frustrating, but it'll be fine. Hopefully it doesn't mess up the video. So last time we talked about the universal property that we had for polynomials. So that works for multiple variables as well. So if we have a ring homomorphism, again from F from A to B, but now we take finitely many elements of B, then there exists a unique ring homomorphism, which is evaluation at with respect to F on B1 through Bn, and it goes from this ring of polynomial. Oh, by the way, this is multiplication, and you use addition the way that you would expect it to work, and that gives this a ring structure. So anyways, we have a unique ring homomorphism, which sends the sum of a alpha x to the alpha to, well, we just take the a alphas and evaluate them at f, evaluate f at a alpha, and then we basically evaluate x at b. Like if you write like b, like an element b as a multi-index of like b1 through bn, well, that's not really a good way to say it. Yeah, the best way to think of it is just the way that it's written here. But you sort of implicitly think of x to the alpha as x1 to the alpha 1 through xn to the alpha n. And you basically just replace these xi's with the bi's. So yeah. And again, like last time, we're not going to prove that. I guess the proof isn't super important, but you can do it. Anyways, so we also have a definition of algebraic, but this definition is a little different. We say that these numbers are algebraically independent over A if the kernel of this map is 0, and otherwise they're algebraically dependent. So if they're algebraically independent, or let's see here. So if they're algebraically dependent, that means that you can like take a polynomial. You can take a polynomial and evaluate it at these particular elements and get 0. Like you can find a polynomial that lets you do that, that lets you get to 0. A non-trivial polynomial that lets you get to 0. So yeah, and there's a lot of stuff about this that we don't know, like just taking very simple cases like A is equal to B again, like I was talking about last time, and F being just the identity map. And if you just take like B1 and B2, just do two variables. I'm pretty sure most numbers we don't know if they're algebraically independent. Like I'm pretty sure we don't know if like E and pi are algebraically independent or if they're algebraically dependent, which because of how important those numbers are, you would expect us to know that by now. Although it did take a very long time to prove things like that pi is transcendental and that E is transcendental, and this appears to be like a whole nother thing. But yeah, this is sort of a source of like sort of interesting problems that you can sort of like think about at a really low level. And such problems are kind of neat. And we can actually generalize this stuff about polynomials and finite variables if we replace these x1 through xn, if we in a sense replace them with elements in a monoid. So if we take a commutative ring A and a monoid M, we just take, we let A adjoin M be the set of all functions from M into A, such that f of M is 0 for all but finitely many indices, i.e. the set of m's such that f of m is non-zero is finite. This is really weird to choose here. Typically I use like a colon. Algebraists tend to use like a vertical line like I've done here. I didn't want to use a colon because there's a colon here, and I didn't want to use a vertical line because there's a vertical line here, so there's like no good way to do this notation. But anyways, this works. So yeah, we can give it a ring structure. F plus g of m is fm plus gm. Then f times g of m is, well, what we do is we sum over all elements y and z and m whose product is m of fy times gz. And typically how you would write this is I think there's a nicer way of writing this when M is a group, but that doesn't work if you don't have inverses. And so you have to do this sort of strange looking definition. But there's sort of inverses hidden in here, like things that you would like to be inverses, but we've sort of done them in a way that's not using inverses so that we can do them in a monoid. So anyways, we call this a monoid ring. If M is a group, it's a group ring, and you can do stuff with that. And yeah, so here's some stuff, and that finishes this lecture.